right, you guys, so we're going to go over heat and energy for temperature, and I want just to note a couple of different things with heat and temperature. Heat is the total kinetic energy transfer from one substance to another, while temperature is just the average kinetic energy of the particles in the substance. What does that even mean? OMG. So heat just basically means that you have something moving from one item to another item. Example, you have this pot right here. So your heat is transferring from the stove top to the pot and from the pot to the water, right? And that water is starting to retain heat. And as it retains a certain amount of heat, when it reaches its heat capacity, it's then going to start to boil because the temperature now of that water has increased, right? So boiling water boils at 100 degrees Celsius. That is the temperature of the water. We could look at the water, look at its boiling, and say the water is at 100 degrees Celsius. The water in the pot and the water in the spoon both have the same temperature, 100 degrees Celsius. Yet, the heat capacity of both of these, or I'm sorry, the specific heat of both of these, not heat capacity, the specific heat of both of these are different, as the pot has a lot more water, so therefore is able to retain a lot more heat, while the spoon itself has very little water in it and cannot retain that much heat. The heat will escape from that water a lot faster. So if we want to write differences, there is heat. Okay. And heat is just the total kinetic energy transfer from one substance to another. So if you had a container and the container is divided, heat is basically going to go from A to B. Okay, it's transferring heat from one container to another, while temperature is different. And actually, before I go into temperature, just a little bit more about heat. Heat transfers from hot to cold, by the way. That's the way it transfers. The heat is going to go to the more cold. And the unit for heat is joules, the J. Okay. All right. Now, we remember we use Q to denote our heat. Temperature is different. Temperature is the average kinetic energy in a particle. So that is different. That means if I have the same two containers, okay, remember we have A and B. Okay. And in this case, A, we have, it's hot, right? So we have a lot of motion happening here. A lot of motion. The energy is moving in here. It's the average energy moving here. So we have fast moving particles. And the faster the particles move, therefore you're going to get, right? Actually, I was going to say, the more heat you apply to something, the faster your particles are going to move. So therefore, these are moving faster. That's because they have more heat. Okay? So it increases, speed increases when you heat it, and so does the temperature. The temperature also increases. Yet in B is going to be a little bit different because we said that B is cold. So B, you're going to have some very, very slow moving particles, okay? Compared to A, where A, everything is kind of like ding, ding, moving everywhere wherever they want to go, okay? And they're moving like fast. They're everywhere, right? B is a lot slower, and that's because it's colder. So these are slow moving particles. Remember, this is hot and this is cold. And these slow moving particles will speed decrease. So you have a decrease in speed. And that's because you have a decrease in heat. and therefore you're going to have a decrease in temperature. Okay, so that's the difference between heat and temperature. And temperature, our units of temperature are going to be Kelvin, which is K, and Celsius, which is C. And we denote temperature with a T. And we denote the change in temperature with a delta T. So change in temperature is denoted by a delta T. Sure we don't confuse all of these. Right? And delta T is going to equal to the final temperature minus your initial temperature. Okay, so final minus initial on temperatures, and that's going to be your delta T. Okay, so now that we know the differences between those, let's go ahead and talk about specific heat and heat capacity. Those are going to be the two other things we're going to go through right now, and then we'll go into calorimetry. So let's grab a different color. We have specific heat, and we're going to have heat capacity. So every substance has a unique heat and temperature value. So specific heat and heat capacity. So let me write that, what I just said. Every substance has a unique, make sure you guys can see it, heat and temperature value. So that means we could look up a certain substance and be like, oh, that's the specific heat of that specific substance. Okay. So specific heat, let's just quickly before we get into it, like look into this example. 1 kilogram of water, 1 kilogram of iron. Same mass, different substance. If you have 1,000 calories of heat energy and you add it to water, your temperature is only going to increase by 1 degree Celsius. Very specific number. If you take that same heat and add 1,000 calories to the 1 kilogram of iron, you'll notice that your temperature increases 9 times, like almost tenfold, by 9.3, right? By 9.3. And that has to do with the specific heat value. And the specific heat value for every substance is going to be different. So specific heat is going to be the amount of heat required to raise the temperature of 1 gram of water by 1 degree Celsius. Okay. Or material, I guess in this case. Right, let's go ahead and write these down. This is very important for us to know. So, specific heat is going to be the amount of heat required to raise the temperature of 1 gram, very specific, 1 gram of material by 1 degree Celsius. Right. So very specific, and then let's go ahead and write that equation out. So I'm going to write SH right now. Actually, no, I'm not going to write this SH. I'm going to write the whole thing out because I have a plan. Specific heat is equal to the heat divided by, remember we're using mass and we're using temperature, so divided by the mass times the change in temperature. So this is our equation for specific heat. Now let's go ahead and write all the letterings that we need that's going to go with this. All right, so specific heat is equal to the heat divided by the mass times the change in temperature. That is specific heat. Our mass is this one right there. Our change in temperature is right here. And our heat is our Q value. Okay. So that's specific heat. And this equation right here can be rewritten in a format that you're going to probably use more often, like this. Q is equal to MS delta T. Heat is equal to mass times the specific heat times the change in temperature. The specific heat value is going to be usually a known value or a given value usually. Sometimes though they'll have to give you all of these in order for you to find this. But if you know what the substance is, you should be able to figure out the specific heat by looking it up. So you could usually look it up. Can be looked up for common things. And what I mean about that is, for example, water has a very, very specific heat. So water specific heat is 4.184. If you look at this chart right here, this is specific heat values of several materials in joules. And water is 4.184. So that's actually a very, very important number to know. So the specific heat of water is 4.184 joules per gram degree Celsius. And then the reason I tell you that that is an important number is because water is a universal substance that we use, and water is inside of us, and water actually controls the temperature of our climate, and it allows us to live in different climates. If you notice, nothing else has a comparable value to the specific heat of water. Ethanol, which is alcohol, slightly, but still doesn't have that same specific heat of water. That means that water has a very, very high probability, water has a high ability to retain heat. So the higher the specific heat value, the more capable a substance is to retain heat, is able to retain heat. Okay, you could heat up metal and water to 100 degrees Celsius and the metal will cool off right away, but your water won't cool off that fast. It'll take your water a while to cool off. Oh, and with these images, what I want to say with this one is that because water has a high specific heat and water is inside of our bodies, right, where bodies are predominantly made out of water, we can live in really, really cold areas and in really, really warm areas because water maintains our body temperature stable. And that's what water actually, people who live in the coastal areas, the reason that the coastal areas have a good climate is because they're surrounded by water, and water tends to keep everything nice and stable. For those who live up north and you're like, we're surrounded by water, but we're really cold. Well, it would actually be a lot colder if you didn't have the water there. All right, let's go ahead and look at this problem. How many kilojoules of heat are required to raise the temperature 120 grams of water by 5 degrees Celsius? All right, so if we recall our equation, Q is equal to MS delta T. Okay, so we're looking for specific heat. We want this, and we want it in kilojoules. Yes, kilojoules in kJ. All right, so the mass is given to us as 120 grams. The S is going to be of water. And we said that was 4.184 joules per gram degree Celsius. And our change in temperature, well, we're going to change our temperature by 5 degrees Celsius. All right, now that we have all this information, let's go ahead and plug it in. Q is equal to 120 grams times our S, which is 4.184 joules per gram degree Celsius, times our temperature of 5 degrees Celsius. Celsius cancels out, grams cancels out, and we're left with joules. So let's go ahead and do the math, or just look it up. Just kidding. Right here. And you know what? Just because I always like to verify my math, sometimes the PowerPoints can be a little bit off. So 120 times 4.184 times 5. Okay, I got 2510. So we got Q is equal to 2510.4. And this is in the unit of joules. However, this is asking me to give it in kilojoules. Okay. Before I do that, actually no, let's go ahead and do it in kilojoules, and then we're going to transfer it to the correct number of significant figures. Okay. So kilojoules, 1,000 joules equals 1 kilojoule. So therefore, if I have this number here, and I turn this equality into a conversion, this joules, 1 kilojoule over 1,000 joules, I could cancel out joules, right? And then I end up with 2.5104 kilojoules as my final answer. Actually, not the final answer, because now we're going to look at significant figures. We have 4 significant figures here, but only 2 there. So we have to put this into significant figures, which is going to be where that 5 is at. So therefore, my Q is actually going to be 2.5 kilojoules. And that's the amount of heat required to raise the temperature of 120 grams of water by 5 degrees Celsius. Right. Now that we've talked about specific heat, we're going to talk about something else. And this other option is going to be called the heat capacity. Now, heat capacity is slightly different because heat capacity does not involve mass. So if you notice both of our numbers, in specific heat, you have M for mass. In heat capacity, there is no M for mass. Okay. Specific heat, we use it because we know what substance we have, right? We know what it is. It's a simple object or simple substance, and we could take the mass of it. However, in this heat capacity value, we can't really take the mass of a reaction that's occurring. So like how much of the gas was produced or this or that. So we can't do that in process, right? So therefore, we're going to use the heat capacity. This is more for like our chemical reactions. And let's go ahead and write down our heat capacity. Okay. I was going to write it on the back, but then I'm like, yeah. Heat capacity. Okay. So heat capacity is the amount of heat required. Let's see. The amount of heat required to raise temperature by 1 degree Celsius. So it doesn't say to raise the temperature of 1 gram. It just says to raise the temperature in by 1 degree Celsius. So therefore, heat capacity is going to equal to Q over delta T. And the other way that we're going to see this, you're going to see heat capacity is denoted with a C. So you're going to see C is equal to Q divided by delta T. And Q is equal to C delta T. Okay. Heat is equal to cat. That's one way of seeing it. All right. Now let's go ahead and look at this problem right here. When filled with water, a large reaction vessel in a chemical plant has a heat capacity of 5.41 times 10 to the 5th kilojoules per degree Celsius. How many kilojoules of heat, so we're looking for kilojoules, are required to heat this entire vessel from 25 to 48.2 degrees Celsius? All right, let's go again and get this done then. So our example problem, it says we have a large water vessel and chemical, so heat capacity, so C is 5.41 times 10 to the 5th kilojoules per degree Celsius. We're looking for kilojoules of heat, so we're looking for Q. It is unknown, and we want it in kilojoules. Our change in temperature, it goes from 25 to 48.2. So change in temperature is always final minus initial. Okay. So that one's 48.2 minus 25, 23.2. All right, now that we have this, we're going to go ahead and plug all of this into our equation. So I'm going to use this one because I'm looking for Q. Q is equal to 0.41 times 10 to the 5th kilojoules per degree Celsius times my change in temperature, which is 23.2 degrees Celsius. All right, let's verify and make sure that we're actually on the correct path. All right, our change in temperature is correct, and we set up the problem correctly. Canceling out the units of degrees Celsius, we're left with kilojoules. That's exactly what we want. We're going to multiply them together, and I'm going to go ahead and do this in my fancy dancy calculator. Times 23.2. All right, and I get this ginormous number. However, we all know we don't leave our answers that way. We have to convert them into scientific notation and into the correct number of significant figures. The correct number of significant figures in this case is 1, 2, 3, 1, 2, 3, 1, 2, 3. 3 significant figures. So first, let's see, in scientific, actually, 3 significant figures is going to be 1, 2, 3. So that means this 5 is going to round that 5 up to a 6. And let's see how many we have to move this understood decimal over. 1, 2, 3, 4, 5, 6, 7. So we get 1.26 times 10 to the 7th kilojoules. And that's exactly what we got on our PowerPoint. So we are a step ahead. All right, recapping, specific heat uses mass. Heat capacity does not use mass. Specific heat is used for a specific item, while heat capacity is more for like a chemical reaction that's occurring. All right, next step is calorimetry. All right, let's go into calorimetry. Calorimetry. And calorimetry is we're just going to be measuring the amount of water in experiments. So scientists and engineers often need to measure how much heat is being transferred from one item to another item. Experiments that measure the heat flow are called calorimetry experiments. Sometimes we see these as coffee cup calorimetries or bomb calorimetries. In college, you're going to see coffee cup calorimetries. Maybe some of you guys saw those in high school. Bomb calorimeters are mainly going to be at the universities unless you're in a super duper fancy college. Okay. So calorimetry experiments measure the flow of heat. You have coffee cup calorimeter and you have a bomb calorimeter. Okay. Coffee cup is just a cheap way. You just use some coffee cups, and you just need coffee cups, your substance, which is water or something else, and thermometer, something to kind of wrap it with. Oh, there you go. This is what a coffee cup calorimeter looks like. Okay. So in calorimetry, you have coffee cup, which is just an insulated cup, coffee cup calorimetry. And you're going to have the other one, which is going to be our bomb calorimetry. All right, so in a coffee cup calorimetry, let's kind of go through a little bit of what it's going to look like inside. Okay. We have a cup. And inside the cup is going to be our water. And we're going to end up, actually, we heat up the water. We find out the temperature of the water. So inside of this is going to be a substance that we're going to throw in here. Most of the time it's an unknown substance. Sometimes it's known. Okay, so you're going to have a substance. They say it's iron. All right, Fe. Now what this substance is going to do, it's going to transfer its heat out into the water. Okay. Now the reaction goes pretty fast, so you have to make sure that you are constantly recording the temperatures, the changes in temperatures of the water. So remember, heat is the transfer of kinetic energy from one substance to another. Temperature is basically the average kinetic energy of the particles. So how fast are these particles starting to move now that we are transferring heat to it? The entire container is sealed though. So we're sealing the container. Now, usually we just add some more styrofoam cup, like a little bit, and then we put some aluminum foil around it if we want to be like nice and make sure that our experiment is retaining as much heat as possible. Then we're going to do this. Okay. So this is going to be our aluminum foil. Thermometer. Water. Your substance. Okay, so you have to know the water, the temperature. You need to know the temperature initial. So before you put the substance in there, and you need temperature final. And that's after your temperature starts to kind of give you the same numbers and it starts to go down. So this is the temperature, the highest temperature probably. And your substance is going to be the one that's heated and transfers heat. And usually we know the temperature of this substance because we're going to boil it in water. And we're going to boil it in water for like 10 minutes. So that should give you the temperature of this substance right here. So the temperature of your substance. And if it's being boiled for 10 minutes, it's usually going to be about 100 degrees Celsius, usually. Now, this is experimental. Don't take this by hand. This is kind of like experimental value. All right. So it could change depending on the question that they ask you. All right. So what does all this mean right here? It means that the heat of the water is going to equal to the negative heat of the metal. Why? The heat of this water is equal to what this metal is losing, right? So Q of water is equal to Q of the metal. And because the metal is losing heat, we're going to put that negative to indicate that it's lost some heat associated with it. So based on this equation, right, we can see that the specific heat of the metal is equal to the negative of the mass of water times everything else. So let's look at that. So here we have the heat is equal to ms delta T, right? And it's all going to change. So if we plug in the equations, the Q on both sides, we're just going to get this set up. So remember, Q is equal to ms delta T. And this is of our water. And Q of the metal, well, because we lost heat, so it's negative, is going to equal to ms delta T. And this is going to be of your metal substance, or the substance that you threw in there. Okay. So you can't forget about that negative value that you're reaching there. Okay. Now, if we wanted to actually know the specific heat of the metal, then all we're going to do is combine both of these together to find the specific heat of the metal. And that's going to be negative ms delta T divided by m delta T. And because this is the one of the metal, right? These are all metals and this is all water. So all we did was divide this side by m delta T and moved it over so that we could isolate S and find the specific heat of the metal. So this is kind of like a bomb calorimeter works. I love this type of experiments because I love collecting the data and trying to do the math with it. All right, okay, now we have an actual problem. So let's go ahead and look at this problem. A chemist heats up 26 grams of an unknown metal at 100 degrees Celsius, then places it in a coffee cup calorimeter containing 52.1 grams of water at an initial temperature of 20 degrees Celsius. After some time, both the metal and the water reach an equal temperature of 24 degrees Celsius. What is the specific heat of the metal? All right, and it gives us the specific heat of water. SW is the specific heat of water. So I want some extra space, so I'm just going to work on this side of my paper. Okay. And let's figure out what we got. Okay. So the specific heat of water is equal to 4.184 joules per gram degrees Celsius. What else does it give us? It has 26 grams of an unknown substance. Specific heat of the metal is unknown. Okay. Let's just do mass of water and then mass of our metal. We have 26.0 grams of this. The temperature initial of my metal is 100 degrees Celsius. It places it in a coffee cup calorimeter containing 52.1 grams of water. At an initial temperature of 20 degrees Celsius. So temperature initial is equal to 20 degrees Celsius. After some time, both the metal and water reach an equal temperature of 24 degrees Celsius. So temperature final is equal to 24 degrees Celsius. And that's going to be the same for both because it's an equal temperature. Okay. What is the specific heat of the metal? All right, well, it looks like we have everything that we need here. So let's go ahead and write our equations down. The specific heat of the metal is going to equal to mc delta T. What did we write down? Oh, it's right here. Is equal to ms delta T of water divided by m delta T of our metal. Okay. Now we're just going to plug everything in. So the specific heat of the metal is equal to everything we just found out about water, 52.1 grams times 4.184 joules per grams degrees Celsius. Make sure you put your units down because that allows you to figure out if your units could actually cancel out, if you're missing a step, or if you do something wrong. All right, our delta T, our change in temperature of water, is 24 minus 20. Final minus initial. And all of that is going to be divided by our metal information. So the mass of my metal, which is 26.0 grams. And the change in temperature of my metal, which is going to be 24 minus 100. All right. So the specific heat of my metal, now we could just start calculating some items here. So 24 minus 20 is just going to be 4 degrees Celsius. 24 minus 100, I should be able to do that in my head, but it can't. So that is 76 degrees Celsius. That's going to make that a lot easier. Take our trusty handy dandy calculator. We get, I'll put it here so you guys can see. Let's see. $52.1 times 4.184 times 4. Okay, that's that answer. And you know what? I'm going to write it down even though I'm not going to finish this yet. I'm going to write it down in case I need it. All right. We're going to take that and we're going to divide this entire answer. And I'm going to put parentheses now by 26 times 76 and parentheses. Okay. And we get 0.441268. And I'll double check our units, make sure that we actually got our units correct. All right, so Celsius cancels out with Celsius there. Grams cancels out with grams. And I am left with joules per gram degree Celsius. Now, we need to also convert this into proper significant figures. So let's look at our question. We have 3, 4, 3, 3, 3. So we need 3 significant figures. That's going to stop us right there. That 2 does not round up that 1. So therefore, specific heat of our metal is going to be 0.441 joules per gram degree Celsius. All right, let's see how well we did. Okay. All right. We ended up with 0.44 joules per gram degree Celsius. Now, some things that I saw here, and I didn't write them down here, just because I skipped the steps. Mathematically, you still had the negative here, and this is going to be negative 76. So you're going to have a negative and a negative, which is going to become a positive. That's why our answer is positive. Okay, so negative and negative equal positive, positive answer right here. Okay. Now you can figure out what your metal is by looking it up, and you can say, okay, let's see what the specific heat of it might be. Maybe it's here. Let's see. 0.44. All right, we have chromium at 0.449, and we have iron at 0.449, and nickel, even smaller, at 0.444. So the closest answer that we can actually get for this one is going to be nickel at 0.444. So let's go on to the next little spot that we have. Okay, if you look at a second example involving a coffee cup calorimeter, in this case, we have ammonium chloride, right? And it absorbs heat when it dissolves in water. So that's why it gets really cold, and we use them in those icy cold packs. So instant cold packs is usually what we call it. It's an endothermic process, right? This is an endothermic process. And this is the equation. Heat plus ammonium chloride gives you aqueous ammonium chloride. And it's cold, right? And we usually use those ice packs when we need them. So how much does the temperature drop when we dissolve ammonium chloride in water? Of course, it's all going to depend on how much ammonium chloride you have, and how much water you're going to be using. But you can measure the amount of heat that ammonium chloride is going to absorb using a coffee cup calorimeter experiment. Okay. So you're just going to fill it with water, you're going to add your ammonium chloride, and you're going to measure the changes in temperature. And you're going to apply the same equations that we looked at. So Q of the solid is equal to the negative Q of the aqueous, right? This is our solid, and the aqueous, it turned into a liquid later. So therefore, Q of the solid is equal to the mass of the aqueous times the specific heat of the aqueous times the change in temperature of the aqueous. Okay. No, what was I going to say? Okay. Now that we know that, we're going to just take another look at it, and this time through a little word problem kind of way, and then try to solve that problem. So in this example, you have a 10.4 gram sample of ammonium chloride, and it's being combined with 100 grams of water in a coffee cup calorimeter. It's going to cause the water temperature to decrease, that means go down, by 6.20 degrees Celsius. Based on this, how much heat energy was required to dissolve the sample of ammonium chloride? So we want to know how much heat was required to dissolve it. And we want to calculate the heat of the solution for ammonium chloride in kilojoules per mole. So in this example, ammonium chloride absorbs heat as it dissolves, right? And that was based on the last equation that we saw, that it was like heat plus ammonium chloride equals ammonium chloride aqueous. The amount of heat absorbed by the solid is equal to the amount of heat lost from the aqueous solution, right? So what the heat that increased in one is the heat that was lost in the other. Okay, it goes somewhere. It doesn't get destroyed. Remember, law of conservation of energy. Energy cannot be created nor destroyed. Heat is a form of energy. So the mass of the resulting solution of our aqueous includes both the water and the dissolved ammonium chloride. So you're going to write it as this. So this is our ammonium chloride plus our water combined together, and is going to give us this mass right here, 110.4 grams. Because the solution is mostly water, you're going to use the specific heat capacity of water. Okay, and that's because it's mainly water, 100 grams of water. So the change in temperature of the aqueous solution is minus 6.2 degrees Celsius. Okay, that's our change in temperature. So to solve the problem, we're going to plug everything into our equation. So the heat of the solid is equal to the negative sign, right? Because there's heat moving, heat being lost. So the aqueous solution is the one that lost its heat, right? It's anyways, the aqueous solution is colder. Sorry, I didn't lose. It's absorbing it. It's absorbing heat, and so it's getting colder. All right. The mass of water plus our ammonium chloride times the specific heat of water times the change in temperature. Cancel out all your units. Make sure grams cancels out with grams, Celsius with Celsius, and we're left with joules. Now, it's asking us to give our final answer in kilojoules. So we're going to go ahead and change it to kilojoules by dividing it by 1,000. Next part, calculate the heat of solution for ammonium chloride. So we have 10.4 grams of ammonium chloride. And now we're going to use the formula mass of ammonium chloride, right? And grams are going to cancel out, and we're going to be left with moles. Why did we do that? Because it wants it in kilojoules per mole. It doesn't want kilojoules per gram. It wants kilojoules per mole. All right, so we ended up with 0.94 moles of ammonium chloride. So now that we have this, we're just going to take our first answer and divide it by the number of moles of ammonium chloride, and we're going to get 14.7 kilojoules per mole as the heat of solution of ammonium chloride being calculated, right, based on everything we did. So one more time, the reason we use the formula mass is to get rid of grams and to get to moles. And we did that because the question says it wants kilojoules per mole. All right. Finally, we have a bomb calorimeter. So a bomb calorimeter is slightly different from a coffee cup calorimeter. A bomb calorimeter is more controlled. Um, it measures the heat of the reaction for fuels and other high energy chemical changes. In a bomb calorimeter, a test sample is placed in a heavy steel metal container. So here's your heavy steel metal container, and then inside is another steel metal container, and then you're going to place your sample inside of it. Outside of the container, you're going to fill it with water. So all of this is filled with water, and you're going to put a thermometer, and that's going to allow you to take constant temperatures. You'll notice that you have ignition wires connecting from the outside of your container all the way to the inside of the container, and that helps detonate the reaction. And when I mean detonate, it's like boom, kaboom, right? It's detonating it. The gases produced inside of it can expand, so the energy is going to be released in the form of heat. Okay? Remember, if you can't expand, if you can't move that piston, then everything's going to get transferred as heat. Using the heat capacity for the calorimeter, the amount of energy produced in the reaction can be determined. So you could determine how much of that energy is being used. So in this example, we would place a small sample of ethanol and excess oxygen inside the bomb calorimeter. We would then ignite the sample inside the container and measure how much of that temperature of the calorimeter has increased, right? Just like we did in the coffee cup calorimetry. So it goes boom, heat gets released. As heat gets released here, that causes the particles to move faster. And as the particles move faster, your temperature goes up. Oh, okay. So, sorry, I started clicking. All right, we're going to go over now this other problem right here. It says a chemist places a 20-gram sample of ethanol inside a bomb calorimeter with a known heat capacity of 28.72 kilojoules per degree Celsius. When the ethanol ignites, the temperature of the calorimeter rises from 22 to 42.74. How much heat did the ethanol release? And calculate the energy released in kilojoules per gram of ethanol. All right, you guys. So let's go ahead and solve this problem that we have here. Okay. We're going to write all our information down. So we have 20-gram sample of ethanol. And I'm just going to put Al for alcohol inside the bomb calorimeter. So that's what's in the sample inside. With a known heat capacity of, so C, mass is this, mass of our alcohol. The heat capacity of our alcohol is 28.72 kilojoules per degree Celsius. When the ethanol ignites, the temperature of the calorimeter rises from 22 to 42 point something. All right, so the delta T of our calorimeter goes from 42.74 degrees Celsius. It goes from 22 to 42 degrees Celsius. All right, so let's figure out what our change in temperature is. We got 42.74 minus 22.04. That gives us a change in temperature of 20.7 degrees Celsius. It says how much heat did the ethanol release, and calculate the energy released in kilojoules per gram of ethanol. All right, so the first thing is write our data down, which is what we did. We wrote all our data down. Now we know it's asking for heat. So heat is equal to the heat capacity times the change in temperature. Heat is going to equal to our heat capacity of 28.72 kilojoules per degree Celsius, right? And we're going to multiply that by our change in temperature. And the change of temperature we calculated above here as 20.7. Okay. Make sure your units cancel out. Forgot to write the unit here. Degrees Celsius cancels out with degrees Celsius, and we're left with kilojoules. And we're going to do the math. Like I said, always verify the numbers here. You never know. So I have that 20.7 I'll multiply it by the 28.72. I get 594.504 kilojoules. Okay, now we know that's not the correct number of significant figures, so we still need to make sure that we turn that into the correct number of significant figures. Now the final question says calculate the energy released in kilojoules per gram of ethanol. So we used 20 grams of those ethanol. Here is the kilojoules. So we're going to take our 594.504 kilojoules and we're going to divide it per grams. So how many grams of the ethanol we have. So the number divided by 20, and we get 29.7252 kilojoules per gram. Now the final steps that we're going to do in this is actually turn everything in proper number of significant figures. We have 3, 4, 4, 4. So we're going to be in 3 significant figures. So the final answer here is going to stop there. That's going to round up. So it's going to be 595 kilojoules. And this one, same thing. We're going to go into 1, 2, 3. The 2 does not round up, that's 7. So 29.7 kilojoules per gram. Right, let's see how we did. Right, and so the equations are quite simple. It's all a matter of basically making sure that you put your numbers all in the correct spot, so you're not mixing them up, right? Making sure you have your mass, your specific heat, or your heat capacity written down appropriately. Because if you don't, then you end up mixing the numbers up, right? So write them out, take a bit of the time to do that, and then you should be able to solve your problems because you know what the equations are. All right, let's go into this last step. Heat, energy, and chemical reactions. It says chemical reactions involve changes in energy, and the energy of a reaction is an extensive property. Okay, so let's write some of this down. This is the next little section. So it's 8.3, and it's called heat, energy, and chemical reactions. So chemical reactions involve changes in energy. So we already know that, right? Making and breaking bonds, that all is a chemical reaction involving energy changes. And the energy of a reaction is extensive property. So energy is an extensive property. Okay, so what extensive property means, it means it depends on the quantity. That's basically how much. Campfire versus a forest fire kind of thing, right? A campfire is much smaller, a forest fire is much bigger. So you're going to release more energy because you have more to burn. Right. Let's look at fuel value. Okay. So it's the amount of energy that can be produced by the combustion of material. Okay. Okay, the amount of energy that can be produced by combustion material. So we had a couple of these. So you see methane, propane, butane, all of these different ones, right? And what I want you to notice is which one has a higher fuel value. That means which one's going to release more energy. And as we can see here, methane has the highest fuel value of 55.5. So it's going to release more energy than your other ones, right? While wood, in this case, only releases 18.9 kilojoules of energy, right? So wood is the most common product that we use, but as you can see, it doesn't release as much energy as methane gas would release. Okay? All right. Now we're going to look into something called the reaction of enthalpy. So reactions of enthalpy is the amount of heat energy absorbed or released in a chemical reaction, but the chemical reaction has to be at a constant pressure, right? So we can't remove that constant pressure. One of the most important measures of energy change in the reaction will be your enthalpy. Okay. So let's go ahead and write our enthalpy down. So enthalpy. And enthalpy is denoted by delta H of the reaction. Okay. And we say it's the amount of heat energy absorbed or released. Absorbed or released in a chemical reaction at constant pressure. All right. So what constant pressure means, this right here, it basically means it does not change. Okay. So does not change. So I want you guys to notice the sign of the reaction, right? And in this case, you're going to notice that the sign is going to be negative. That means that heat is released from the system, okay? So the reaction, if heat is being released, we learned that that's exothermic, to exit, right? So heat is being released. Um, the reaction enthalpy relates the heat change to the number of moles of the reactants and products. So you have to know how many moles in products you have, the quantity value. So in the equation, you're going to see C2H6O right here, our ethanol, and it releases about 1,300 kilojoules of heat when it's burning. The reaction enthalpy is related to the number of moles of each reactant or product. And remember, those molar coefficients, those are the coefficients on your balanced chemical equation. Okay. All right. So if we look at this even further, we have our enthalpy in being released in 1 mole of C2H6O, so in 1 mole of our ethanol, right? Or this is also the enthalpy being released in 3 moles of our oxygen, because this is the enthalpy for the entire reaction, right? This is the enthalpy of 2 moles of CO2, and you guessed it, 3 moles of H2O, right? The enthalpy of the reaction allows you to relate the heat changes in the reaction to the amount of any substance involved in that reaction, right? So that's important to note, because sometimes we'll read an equation, we're like, we don't know what to use. What value do I use? It only gave me enthalpy of the reaction. It doesn't give me the enthalpy of anything else. Well, now you know that it relates to the entire equation. Now there's a couple things we're going to write here now to take in our notes. A positive delta H versus a negative delta H. Okay, so remember, if it's positive, it's absorbing energy, and this is endothermic. And if it's negative, it's exothermic. Okay, so this means energy is being absorbed, and this one means energy is being released. Okay, and remember, this is the value for the entire reaction. So is for entire reaction. So let's go ahead and go over this problem right here. How much heat will be released with a combustion reaction of 789.0 grams of ethanol, which is our C2H6O. Now, something very important that it told us, it didn't really give us a lot of information, but at the same time, it did if we can decipher it. It gave us the mass of ethanol, and it told us that it's a combustion reaction. So combustion reaction equals exothermic. All right, it's going to release heat, and therefore our delta H is negative. Sometimes it won't tell you that. In this case, it already gave us our negative delta H value. All right, this is wonderful. So we're looking for Q of ethanol, right? The heat of ethanol. We know that the delta H of our reaction is negative 1,368 kilojoules. And this is the reaction that's going to be present. Remember, this is of the entire reaction and of the molar coefficients if you take them into little pieces. So if we're looking at ethanol, we have 1 molar coefficient, 1 ethanol in the entire reaction. So this is the amount of, so delta H for our ethanol is going to be negative 1,368 kilojoules in 1 mole of ethanol. Okay, and that's because our reaction has the 1 as the coefficient. So how do we actually report this in heat without this mole value there? We want to get rid of that mole value. We're going to do a little bit of our dimensional analysis here now. So we're going to take our grams and we're going to convert our grams into moles. So we're going to go from grams to moles, and then from moles to our energy value. Okay, those are the steps that we're going to do. So here we have we have 789.0 grams of ethanol, C2H, H6O. Okay, and we're going to convert it into moles by using the molar mass. So in 1 mole, what we want goes on top, and the grams of our alcohol, I'm just going to ETH, okay, are going to go on the bottom. We have to figure out what that is. Well, carbon is roughly 12, and there is 2 of those. So 12 times 2 is going to be 24. Oxygen is roughly 16, and there is 1 of those. So that's just going to be 16. And hydrogen is about 1, and there is 6 of those. So that is 6. If we add all of those together, that is going to be 16, carry the 1, 2, 3, 4, 46. So 46 grams. This allows grams of ethanol to cancel out with grams of ethanol, and we're left with 1 mole of ethanol, right? We don't want moles of ethanol, and that's wonderful that we have this because that's what we're going to use to cancel this out. So now that we went from grams to moles, we're going to go from moles to energy. At that final step, our energy value is negative 1,368 kilojoules in 1 mole of ethanol. 1 mole of ethanol cancels out. We're left with kilojoules, which is our heat value, and that's what we want. Let's just double check to see if we've been doing our work correctly. Grams to moles, moles to energy. Right? They didn't round, I rounded. And with a final answer given to us as negative 2.34, I am going to verify this and put it into my calculator because it's always a good practice to verify all your work. So that. Okay, and I get 2,346,4.1739 kilojoules. Now, I wrote all of this down. That does not mean that's going to be my final answer. We're not ridiculous, right? We know we're not that accurate. We have to report our answer in 4 significant figures. 1, 2, 3, 4. 1, 2, 3, 4. That's right here. This 4 does not round up that 6. So we're left with 2, 3, 4, 6, 0 kilojoules. However, we already know that we still don't report our answers like this. We report our answers in scientific notation. Big answers in scientific and small ones in scientific. So we're going to take this decimal and move it over. 1, 2, 3, 4. So, oh, and this is negative. These are negative. We get negative 2.346 times 10 to the, what was that? 1, 2, 3, 4. To the 4th power. And it's in kilojoules right there. Verified my answer really quick, and boom. Right, pretty much correct. The difference is why I got a 6 and they got a 2 is because they didn't round, and I rounded just for time's sake. Their answer is actually been more accurate because they didn't round. And that is the amount of heat energy that was released. You notice that when they wrote heat energy released, they dropped the negative sign, okay? Because we're already writing down that it got released, okay? So if you don't write down that it got released, you don't have to put, you have to put the negative sign, and that tells everyone it's negative. So for this part right here, it's the reaction, heat is being released, okay? All right, let's go ahead and move on to one last problem. Many manufacturers produce hydrogen gas from methane gas, as shown in the reaction below. Where am I? This reaction is endothermic with a delta H value of 206.1 kilojoules. Okay, so now we're going to be taking this into different steps. How much heat energy is required to produce 1 kilogram of hydrogen gas? Right. So if you look at it, you have to begin with the kilograms of hydrogen gas. Okay? And to do that, you have to convert it into grams of hydrogen gas. In that way, you can convert grams into moles. Right. So we have 1 kilogram kilograms of hydrogen gas, of H2 gas. And the way we're going to convert it is the same way we've converted everything else, is by using the molar mass. So hydrogen gas is about sorry, my mistake. Before we do this, I'm converting kilograms to grams. I'm thinking incorrectly here. All right, 1.00 kilograms. So we're going to convert that into grams. This is why it's better to write all our steps down and not try to take shortcuts like I just did. All right, and if we recall, there is 1,000 grams in 1 kilogram. Okay, so therefore I'm going to take my 1 kilogram and I'm going to multiply that by 1,000 in order to get rid of the kilograms. And that's going to give me grams of hydrogen gas. Okay. Now, what's going to be our next step? Okay. Now that we have grams of hydrogen gas, our next step is to get moles of hydrogen gas. And that's what we were going to do right up here. The moles of hydrogen gas in 1 mole of H2. And this is going to come from the periodic table, the molar mass. There is about 1.01 grams of H2. Grams of H2 cancel out, and now we're left with moles of hydrogen gas. So then what's going to be our next step after we do this? Okay, the next step is going to be to convert it into our energy value. Now, I want you guys to note something. Okay, in the periodic table, the 1.01 is for one hydrogen atom. We have hydrogen gas, which is diatomic, which means it's H2. And I did not take into account the H2, so therefore this number is actually 2.02 because we have 2 hydrogens. Okay. All right. now that that's done, we're going to go ahead and turn this into our energy value. That is the last step. And our problem says that we have 206.1 kilojoules. So 206.1 kilojoules of heat. And let's look at how many moles of hydrogen gas we have. We have 3 moles of hydrogen gas in our reaction. 3 moles of H2 gas in our reaction. So moles of H2 cancel out, and we're left with our heat value here. That's what we're looking for. We're looking for the amount of heat produced by the hydrogen gas. Let's go ahead and put everything in our calculator. All right, and one more step. Okay, and let's see how we did. I got 3.4, 1, 2, 3, 4 to the 4th power. All right, 3.4 to the 4th power. And this is the giant number that I actually ended up getting. And I'm going to write it out because it's best for us to continue practicing conversions, because if not, we forget how to do those conversions to scientific notation and proper significant figures. The question gives us 4 significant figures here and 3 significant figures here. So our answer is going to be in 3 significant figures and in scientific notation. So that means we're going to stop there at the 0. This 0 here does not round that up. So we're going to go at 1, 2, 3, 4. 3.40 times 10 to the 4th power. That's the number of kilojoules, the heat required for that reaction. So that's going to be our final answer for this one. Okay, so let's go ahead and take a good look at water, because water is one of those that's a little bit different than most other substances. Okay, water does play tricks, especially because of the phase changes that it's going through. So the formation of an aqueous solution, it's always going to involve an enthalpy change, right? And so if you look at this example, you have 2 equations, right? The melting and the freezing, and this describe the enthalpy changes that the water is going through. One is positive and one is negative. You're going to notice that the energy absorbed when ice melts is the opposite of when the energy is released when the water is freezing. Right? That's all it is. But why is that? That's because when something is melting, it's releasing its energy. When it's freezing, it's absorbing energy, right? And it's opposite. When something is melting, it's because it has all that energy inside of it, right? It's moving a lot faster and whatnot. When it's freezing, it's actually oh my goodness, I am so tired that I'm like not thinking straight. When you are melting, you have absorbed energy inside. You've absorbed it, okay? And because you've absorbed the energy, your molecules inside of you are moving a lot faster, causing you to melt. When you're freezing, okay, you're getting cold, it's because you're actually releasing that energy out into the surroundings. So your system is releasing the energy out into the surroundings, and that release of energy is an exothermic process. Okay? And that's what causes water to actually freeze. So this is what I meant when water can be confusing when we think about it, because we're like, what? Exothermic is the release of heat, but yet freezing feels cold, right? So keep that in mind, okay? Freezing, exothermic reaction, the release of energy. Melting is an endothermic reaction, the absorption of energy. Glad I said that a lot slower because it helped us process that information, right? And let's go ahead and actually write that down right here so we don't forget that melting. So this is for water. Make sure that you note that this is for water. So when you're melting, okay, you are in endothermic reaction. Okay, and so that means you're going to go from an H2O solid into your H2O liquid, and you're going to absorb energy. When you are freezing, you're in exothermic reaction, okay, and you're going from H2O liquid to H2O solid, right? And in this case, you're releasing energy when you're freezing. All right, so to quickly summarize, the energy released in a chemical reaction is an extensive property. That means it depends on the substance that it's reacting with. For combustion reactions, we often describe the fuel value, right? So like methanol versus wood or things like that. And that fuel value is the energy that's released in the reaction. Methanol releases more energy than wood, right? We often describe this in kilojoules per gram. The reaction enthalpy relates heat released in a reaction to the balanced equation. So just like we practiced on the last one, where it was like this is the amount of heat released for the reaction, but that can be individualized for every coefficient that's in the reaction. So for every substance that reacts. All right, you guys. Please message me if you need some help or anything like that. I know that this chapter is a little bit more different because it's introducing things that we haven't heard of before, like we haven't heard of calorimetry, we haven't heard of specific heat or heat capacity. But all in all, it's just a little bit of mathematics that we should be able to handle. But if you need help, just send me a screenshot. You know the drill, and I'll reply to you as quickly as I can. Ciao.